Hello, welcome to GCSE Bite Size with me, Chris Smith, and with Ben Valsler. We're from The Naked Scientists. In this podcast, we'll explore the basis of radiation and how it can be used to see inside you and cook your dinner. But first, Ben, tell us about light.
Well, visible light will be the best known type of electromagnetic radiation, although there are many others, from radio waves to gamma rays. They all travel as waves and will all travel through a vacuum at the same speed. That's the speed of light. All forms of electromagnetic radiation behave as waves, and different parts of the spectrum have different wavelengths, so they can behave very differently.
But what actually is a spectrum?
Well, you'll have probably seen a spectrum if you've ever looked at light reflected off a CD and seen lots of colours, or if you've ever played with a prism and projected what looks like a rainbow onto a wall. This works because the white light is made up of a mixture of lots of different colours, or wavelengths of light. When light enters or leaves the glass of the prism, the blue and violet light is bent much more than the green light, which in turn is bent more than the red, so the different wavelengths are spread out, and this produces a rather beautiful rainbow effect.
So the spectrum is just the different wavelengths of light split up so you can see them?
Yes, but visible light is only a tiny fraction of the whole electromagnetic spectrum. There are many other wavelengths of electromagnetic radiation, both shorter and longer than visible light. We split the spectrum into different types of radiation, but this is just for our convenience, as the spectrum is really continuous, so at the junctions the types tend to blur into one another.
Okay, so what has a shorter wavelength than normal visible light?
Well, just beyond the violet, the short wavelength end of the visible spectrum, you find ultraviolet. If you've ever been to a nightclub and noticed that your clothes are glowing, this is because ultraviolet lights are giving various pigments in your clothes the energy to glow. The shorter wavelength types of ultraviolet in the sun can actually damage your skin cells and give you sunburn, and if you're unlucky, skin cancer. But unlike X-rays, the damage is only to the skin.
X-rays enable you to take pictures of bones though, don't they?
Yes, X-rays are the type of electromagnetic radiation that's used to take the picture of your bones. They have a shorter wavelength than ultraviolet and can go through skin and soft tissue very easily, but they're stopped by metal or bone. Now this means if you shine them on a person, the bones will show up as shadows, which forms the X-ray images that you were used to seeing in hospitals. But it does mean that they can damage any tissue they pass through. This is why doctors, who work with X-ray machines a lot, will wear lead aprons to protect them. X-rays can also be used in a similar way to find cracks in welding, or to find out what's inside a badly rusted archaeological specimen.
And how do you make an X-ray?
Well, X-rays are made by firing electrons into a special target. There's a great deal of kinetic energy in this collision, and some of this is given off as X-rays. This is different from gamma rays, which are given off from radioactive or nuclear processes.
So what are they?
Well, these are one of the types of radiation that radioactive isotopes can give off. They normally have a shorter wavelength than X-rays and have more energy, so you can do more damage to tissues if it's absorbed.
And is there anything with a shorter wavelength than gamma rays?
Well, although electromagnetic radiation can, theoretically, have as short a wavelength as you could imagine, we call all the really short ones gamma rays. So now we should probably look at things with a longer wavelength than light. Just beyond the red end of the spectrum is infrared light.
Well, yes, that's interesting because my phone and my computer says it communicates using infrared, so is that the same thing?
Well, yes, although your phone normally, when you make a phone call, will communicate with microwaves, it can communicate with other phones or with a computer by flashing light in the near infrared. That is the colours of infrared light with a wavelength very similar to visible light, but your eyes are not sensitive to the colour, so you can't see the flashing light. A TV remote works in the same way.
So if that's near infrared light, are there other types too?
Well, yes, as the wavelength gets longer, you move into the thermal infrared. Things at room temperature will glow in this colour, so it's useful for the military or the police if they want to find people or vehicles that are hiding, as even if they're camouflaged, they'll be glowing brightly in the thermal infrared just because they're warm. Infrared light is also known as thermal radiation, as it can transfer heat. Now, beyond the infrared, with a longer wavelength, are microwaves.
And this is where microwave ovens come in.
Yes, that's right. Certain wavelengths of microwaves, usually 10 to 12 centimetres, are strongly absorbed by water and fats. So a microwave oven works on these wavelengths and uses them to put energy into your food. But microwaves are also used in many other ways. They're sent out from a radar, and the echoes coming back can be used to find the position of planes. Some wavelengths will travel through the atmosphere really well, and so they're used to communicate with satellites. And others are used by your mobile phone, and that communicates with a phone mast. Microwaves are very similar to radio waves, although they are more easily stopped by buildings and things like that.
So what are radio waves then?
Well, these are even longer wavelengths than microwaves. They're used to send the signals to your radio and your TV. There are many different wavelengths of radio, varying from tens of centimetres up to 1 or 2 kilometres, although the military does use wavelengths up to thousands of kilometres long to communicate with submarines.
And why do they use ones with such long wavelengths?
Well, the longer the wavelength, the better it diffracts around corners, and the better it will travel through water and rock. So because the Earth is curved, this means that a very short wavelength FM signal only has a range of 30 or 40 kilometres, because it can't travel far over the horizon. But a long wave signal has a range of 500 to 600 miles as it diffracts around the curve. The one exception to this is certain shortwave frequencies, which can reflect off a conducting layer in the atmosphere, called the ionosphere, and this allows them to be picked up thousands of miles away, in the same way you can see round a corner if you put a mirror in the right place.